All right, so 4.1 questions. Let's project the first couple, discuss them. You guys can see those. All right, so number 2 asks, rewrite the following statement so that the likelihood of rain is expressed as a value between 0 and 1. So the probability of rain today is 25%. So what they want is its decimal equivalent or its ratio equivalent. So what's the same thing as 25% in a decimal?
0.25.
So that's what they're looking for. So for number 2, what we know is that 25% is equal to 0.25. You guys know what a percent means? So when I say 25%, that's really what they're talking about. Does that make sense? Cent as in like century. So if you plug that into your calculator, it's going to give you 0.25, isn't it? Also, you know that this fraction simplifies because 25 goes to 100 4 times, right? So, they said both of those answers would work fine, okay? I would just do the decimal because it's easy. You just take this decimal and go left twice, right? That's the same thing as divided by 100. Okay. Number 3 asks, while this exercise was being created, weather.com indicated that there's a 60% chance of rain for the author's home region. Based on that report, which of the following is most reasonable interpretation? So 60% of the author's region will get rain today. The author's region, in the author's region, it'll rain for 60% of the day, or there is a 0.60 probability that the rain will be somewhere in the author's region at some point during the day. So when you look at your phone, you look at weather.com or whatever it might be, the Weather Channel says if there's a 60% chance of rain today, what does that mean? Just 60% of the area is going to get rain? No. Okay, so what that means is there's a 60% chance that it'll rain at least once. Does that make sense?
Yes.
Okay, so what they're saying is C is the right answer because there's going to be a 60% probability, or it's 0.6 probability, that it'll rain somewhere in the author's region that particular day. So really, kind of the idea is at least once. 4, subjective. Oh, I don't ask subjectives on tests, just to let you guys know. Because what they really mean by subjective is kind of just take your best guess. Now, a lot of our best guesses are better than just like a random guess, because we might actually have some kind of previous knowledge. But, we're still just kind of randomly picking a number that seems reasonable. So I don't tend to put subjective on there because I'm going to get, there's 24 students. I'm going to get 24 different answers. All right, and they're all right because it's subjective. Yeah, I know. So I guess you guys would like those on tests, right? All right, so estimate the probability that the next time you turn on the light switch, you'll discover that the bulb does not work. What's your best guess? Do you think it's a 90% chance that the bulb doesn't work?
I'm saying it's 50/50.
How often do bulbs fail?
Not totally true.
Do they fail often? Do they fail 90% of the time?
Nope.
50% of the time? When I turn on these lights, I pretty much expect them to turn on. You guys agree?
Yes.
Like almost every time. I would probably say it's like the probability that it will not turn on is probably going to be somewhere less than 1%, right? It's probably less than 0.1%. It's probably less than 0.001%, right? They don't fail very often. You guys agree? So I would say it's extremely small. So what was their answer? Their answer said, they said that it'll work, that it will not work. So it's almost 100% chance that it's going to work. You guys agree? So their answer was like 0.999. So they said the probability, so number 4, the probability that the light will work, light bulb will work, or turn on, is equal to, I'm going to give a number as close to 100% as possible without being 100%. And we know that our percentages are three significant figures, right? So you have a 0.93 sig figs. What's the closest I can get to 100? Yeah, 999. Does that make sense?
Mm-hmm.
Okay, so I bet you what really that means is 1 in 1,000 times is going to fail, right? Or 999 times out of 1,000 it's going to work. To be honest, it's probably better than that. Have you guys seen LED lights finally die? They're weird, aren't they? They'll turn on sometimes, and then sometimes they won't. And sometimes when you shut off the light, it kind of like glows. It's weird, yeah. I'm having some go, and it's just strange. But I think they lasted like 6 years. Okay, Avogadro's constant. Okay, so if you were asked on a quiz to give the first leftmost non-zero digit of who knows who's a biologist or what is it, a chemist? I can't pronounce that word. Yeah, that's what I'm going with that. Avogadro. I'm destroying it. I apologize to this dead guy. So or girl. So name the first non-zero, the first leftmost non-zero digit of home person's constant, and not knowing the answer, you make a random guess. What's the probability that that your answer is the correct answer of 6? Plus. Yes, right. So. Wow. Sorry. Okay, so what they asked is they want you to make a random guess, right? Does anybody know? I don't either. Okay. Does anybody care?
I didn't know at one point.
You know, yeah, I think yeah, but that's a lifetime ago. So I have no idea. So they said it's the first non-zero number, right? So what you know is that the number is not zero, right? How many numbers are left? How many? Remember, as far as digits, like on your, I don't know, phone or whatever you guys use for digits nowadays. So on like if you're on your dial pad for your phone, you know that there's how many digits? Yeah, because you got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So if you take away 0, how many are left? 9. So the probability of you guessing is 1 out of 9. Does that make sense?
Yeah.
Because there's only one correct answer, right? And out of a total of 9. So really what we see is like the probability of something happening. And so this really comes down to like our classic probability. So the probability of essentially guessing is going to be equal to, our sample space is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Because they said non-zero digit. Now when I write these things, I really mean that there's a total of 9, right? A total of 9 in the bottom.
Yeah.
Okay. And how many are correct? Just one of them. They said the 6 is correct, right? So that is a total of what? On top. If there's 9 on the bottom, how many are on top? 1. Total of 1. So that's why we say there is 1 out of 9 probability. So it's the number that are correct out of the total number that are there. It's like rolling a die, right? How many numbers are on a die?
6.
What's the probability of you rolling a 3? 1 out of 6, right? Because there's only one number 3 out of 6 particular numbers, right? So it's they're all equally likely to happen, but so that's why you use this classical probability. Number 10 says, assume that 50 births are randomly selected. Use subjective judgment to describe the number of births as significantly low, significantly high, neither significantly low or significantly high. Now really remember, significantly low and significantly high, I use like the idea of usual values, right? So like the lowest, like what do you expect these things to be as far as the usual values? So the usual values are going to be between significantly low and significantly high, right? So out of 50 births, how many girls do you expect? Yeah, so there's going to be 25 girls to 50 total, right? Okay. Now we know that there's going to be some randomness in this, so there's going to be some fluctuation, right? So is it going to be exactly 25 every time?
No.
But should it be close?
Yes.
Okay. So it should be really close. So the idea is, how far away is? I want to say this nicely. There's going to be a number that's either below 25 or a number that's above 25 that you're going to consider not possible, or at least very unlikely. So, say I have something happen. We have, what number is this? This is number 10. So this is kind of just some guesses. So I know if there are 50 births, we expect, 25 girls, right? Doesn't mean we're going to get 25 girls, but we know that the probability of having a girl should be, it should be, with the classic probability, it should be, well, this is the girl all over a boy and a girl, right? There is one up top that's correct, and there's 2 on the bottom. So that's that sample space, right? Very similar to what I did on top. So this is 1 out of 2. So I know this is going to be, like you said, that 50-50, so 50%. 3 sig figs, but you don't really need the zeros because they're not relevant. They're not. If I cover that up, it's the exact same number. You guys agree? So you don't really have to put zeros on the end, but you're technically, with probabilities, you usually use 3. Like up here, that's 3 sig figs, right? Okay, but I can't drop any of them because I changed the number, right? Okay. All right, so this is what we expect. So we know that in real life, it's not going to be exactly this, right? If I have 50 births, but I know it's going to be pretty close. So the idea is, what's pretty close? What if I have like 22 girls out of 50?
Is that significantly higher, significantly lower, is it 100%?
Yeah, I'm just kind of curious. You guys consider it's a little lower than what we expect, right? But is it significantly low? Is it outside the range of possibility? No. Okay. So that could totally happen. I would agree. That would actually probably happen pretty frequently. You guys agree? Okay. What if I cover this up and said, how about 20? Still pretty close. You guys agree? What about 18?
It's a little lower.
You guys agree? But we're really using a subjectivity here, right? I think that's a word. We're going with it. So we're using we're basically kind of going off our gut here a little bit. You guys agree? That number is really on the border. You guys agree? So I'm not really sure about that one. It's possibly significantly low. You guys agree? Okay, we're gonna have a real measurement eventually. I keep promising this, but it's coming. Okay. What if I say 10?
That's significantly
Definitely significantly low. You guys agree? There's no doubt about that. But this one is questionable. We know that we can also go above, right? So if I ask, well, what about 30 girls? It is possible to be a little high, like maybe 35 girls. I don't know. It's getting up there, isn't it? Okay, so there's got to be some number in here. I know if I said 40, I'm not sure about that. I know if I say 40,
That's
definitely significantly high. You guys agree? Okay, so let's go back. Let's just do them all. Well, right here, can you guys read that? Probably not very well. We're just going to do them all. So number 9 says 47 girls out of 50 births. Significantly high, significantly low, or kind of what you'd expect?
Significant?
Yeah, extremely significantly high. How about 26? Neither, right? This is definitely the usual values. You guys agree? Okay, how about 23 girls? Yeah, usual values. You guys agree? 5 girls. Yeah, significantly low, outside the range of usual values. You guys agree?
Okay.
All right. 33. 25. I thought they abandoned this book. The X sorts. So they're trying to get a girl. I don't know if this is actually a thing, but I bet you it is. So these,
picking their gender.
yeah, I
It
think
is a thing.
it is, isn't it?
Yeah, Kim Kardashian and Kanye West.
Did they?
Yeah.
Were they successful?
Yeah,
Huh.
they got North. They wanted a girl.
Yeah, all right, man, get it done. So, if you got the money, I guess, whatever you want. That's a hell of a thing, isn't it? Huh. All right, so X sorts, gender selection. Michael Sart's X sort gender selection technique was designed to increase the likelihood of having that a baby will be a girl. Man, I'm not reading well today. At what point before clinical trials of X sort gender selection technique were discontinued? At one point before clinical trials of the X sort gender selection technique were discontinued. 945 births consisted of 879 baby girls and 66 baby boys. Based on these results, what is the probability of a girl born to a couple using the this X sort method? Does it appear that the technique is effective at increasing the likelihood of having a baby that will be a girl? Okay, so let's talk about this. It's kind of nice as we just kind of had something that really related to this. So for number 25, what they've done a trial, right? So we have our two main focuses, our two main approaches to finding probability. One if the probability is equally likely, another if the probability is not equally likely, right? So when they're doing this gender selection method, they're taking it from equally likely to not equally likely. You guys agree? So when we do procedures, we tend to use the other approach. So what we know is probability. Just slide this over. The probability of having a girl in this, let's say, X sort. So if we use the procedure, let's go back to the numbers. The way we know this, actually, we know it's going to be, the number of girls divided by the total number of births, right? You guys agree?
Yes.
Since we're doing some kind of procedure, it's not equally likely to happen, so I can't just do the sample space. I can't just go G over BG, because once they've done this method, now you've changed the probability of having a girl. So how many girls were there? 879 girls. So there were 879 girls. How many births?
945.
How'd you do that?
They give you it.
Oh, does it?
Yeah.
Oh, stinkers. What I was kind of hoping is they would just give you this part, there's this many baby girls and there's this many baby boys in order to figure.
Add them together.
Yeah, that's right. I was kind of hoping they'd make you add these things instead of just, hey, giving you the answer. But okay, fine. So if you add those numbers, you guys agree it's going to be 945?
Yes.
Okay, so on a test, I tend to do that. I'll tend to give you the outcome and its complement, which is not the outcome, and then you'll have to add those two together to get the denominator. So it just happens a lot. I really wanted you guys to add them, but it is what it is. Okay, so what's the probability of having a girl using this procedure?
93%.
Is it brilliant?
Yep.
Okay, 0.930. Okay. Again, we can drop the 0 because the 0 is not a significant figure, but I'm going to always leave them. I like 3 sig figs. So my first non-zero number, I'm going to go 2 beyond that, okay? So 1, 2, 3 numbers. Okay. Does it appear to be effective?
Yeah.
Why is it effective?
Because only 6%. No, yeah, only 7% don't.
Well, because what do we expect? What's the actual probability of having a girl if you don't have the this yeah, because having a girl is equally likely, so it looks like that, right? So it's 1 out of 2, which is 0.500, right? Is this number much bigger than that number? Like a lot bigger. You guys agree? Basically, you would tell me, if I asked you in the previous question, having 879 girls out of 945 births, you guys would have said that is significantly high, right? So it's outside the range of usual values. So if it's outside the range of usual values, the treatment's clearly effective, isn't it? Does that make sense that this can't happen by chance?
Yes.
Okay. What I mean by chance is the range of the usual values from significantly low to significantly high. That's all the possibilities of this having by chance, right? This happened. Man, I gotta have coffee. So that's the fluctuation that you expect. It's going to bounce a little bit back and forth. So if it's outside that expected fluctuation, then you know that it's outside the range of the usual values. Therefore, it's significantly high or significantly low. Since this is significantly high, that means that this thing is effective because we expected that number. 33. I don't want to record anymore. So 33. It's kind of neat, though. That's actually how it has to be done, right? Does it make sense if you really need to know if a treatment is effective? So, for instance, if I want to keep talking about this. What if instead of this was 879? What if this was like
You can't see it.
oh, my bad, thank you. What if instead of that was 879, that was like 555 over 945? What if the problem was that instead?
It seemed a little listed, like it wasn't very useful.
Right. So if I had this 555 divided by 945, what I get is this 0.587. Ugh, made it. Okay, so you guys see that?
Yes.
So if there were 555 girls out of 945 girls, would you say that this is effective?
No.
But wait a second, it's bigger than 50%, right?
But it's not significant.
That's right, it's not significantly bigger, right? This could happen by chance, you guys agree?
Yes.
As opposed to the other one, as opposed to that, which cannot, right? So that's how you have to test treatments. You have to make sure that it's outside the range of that expected fluctuation. I was not a fan of statistics in college until I finally took a couple grad classes in it, and you get a little more appreciation for the science that we're actually doing. Like, it's actual, like, real science. What irritated me before is in mathematics, everything, your answers were all concise, right? Like, you'd get the answer of, like, 5 or maybe 5 grams or something like that. Like, you'd get an actually really concise answer. But in statistics, you get a little fluctuation, right? You get a little plus or minus. But it doesn't, yeah, just because it's not concise doesn't mean it's not realistic, because you can actually nail down the significantly high and significantly low numbers. You can actually find those exactly, and then you can understand that fluctuation. You can see if something's effective or not. It's really quite a clever science. All right, so 33. It says, in these exercises, use the given sample space or construct the required sample space to find the indicated probabilities. So in number 33, it says, use the sample space listing the 8 simple events that are possible when a couple has 3 children. So they actually gave them to you. I will not. Okay? So if you have 3 children, you guys agree you can have all boys? But you can also have 2 girls and a boy. But 2 girls and a boy can happen in multiple ways, right? You can have 2 older boys and 1 younger girl. You can have a middle girl, or you can have there's some other one. Where are you? This should have 2 boys and a girl. I usually try to line them up. I try to do 2 boys and a girl all the way across, and then I do 2 girls and a boy all the way across, just so I can keep track of them, okay? I don't like the way they did it, but it is what it is. So assume that the boys and girls are equally likely, so that that the 8 simple events are equally likely. Find the probability that when a couple has 3 children, there's exactly 1 girl. So what they're asking for in 35, this says, what's the probability of exactly 1 girl? So what I'm going to do is I'm going to list my sample space first, because it'll be easier to work with, and then I can figure out what ones have the 1 girl in it. So you know your sample space of a family with 3 kids is they can have all boys, right? Then they can also have all girls.
Yep.
And then they can have 2 boys and a girl. So, 2 boys and a girl. Or you can have 2 boys and a girl, right? Or you can have 2 boys and a girl, right? And those families are quite different. You guys agree? Okay. And then you can also have 2 girls and a boy. So 2 girls and a boy, 2 girls and a boy, and also 2 girls and a boy. Out of those, which ones have only 1 girl? Is it this one? This one?
Yep.
This one?
Yes.
That one has 1 girl. You guys agree? How about this one?
Yes.
That one has 1 girl. How about this one?
Yes.
That one has 1 girl. So I'd put that in the numerator. I'd say this is, BBG, this is BGB, and this is GBB. Now when I write this, I'm actually talking about the number of things that are there, right? Talking about their count. So how many are up at top? 3. How many are on bottom? 8. There you go. So you get this is 0.375. Remember, probabilities are 3 significant figures, right? You have the first non-zero number and then 2 after that, okay? I think the justification for this is if you put that in a percentage, you get that 1 decimal past the whole number. I think that's why they do that, but it's just 3 sig figs. And that's it.